Picture this. You're sitting in the exam hall, the clock is ticking down, tension is building, and you flip to the final page of your Cambridge Computer Science past paper. Boom! You are face to face with a massive 15-mark scenario-based programming question. Whether you're sitting syllabus 0417, 0478, 2210, or even stepping up to 9618, this is the moment that defines your final grade. Now, I see two types of students in this exact situation. First, we have Alex. Alex panics, overloads the page with raw computer science facts, and dumps a massive, unreadable block of Python code with absolutely zero analysis. Then we have Sam. Sam rushes in, completely misses the specific command word requirements, and forgets the iteration loop entirely. Both students lose massive marks, and it's covered in red pen by the examiner. But today, we are going to change that. Welcome to this explainer. I'm going to show you how to become the wizard of the exam hall. We are going to look at algorithm design not just as a topic, but as a magic spell. A structural framework that, when cast correctly, guarantees you maximum marks. We're transforming those red pen marks into green check marks by showing you the ultimate computer science success blueprint. Let's jump right in. Here is your master blueprint for today's session. We're going to break this down into 6 manageable subtasks. We'll cover the computational thinking framework, mastering top-down design, decoding structure diagrams, the 4 design steps, translating to pseudocode, and finally, the complete process. This agenda isn't just a list, it is the exact chronological strategy you need to tackle those massive exam questions without breaking a sweat. Section 1, the computational thinking framework. Let's look at the absolute core mindset you need to adopt before your pen even touches the paper. It's a massive question, isn't it? How do we actually solve these complex, real-world programming problems without getting completely overwhelmed? When you're staring down a scenario-based question, jumping straight into writing code, like our student Alex did, is a complete recipe for disaster. It leads to tangled logic, missing variables, and dropped marks across all assessment objectives. You wouldn't build a house by just showing up to an empty lot with a hammer and some wood. You need a blueprint. In computer science, creating that blueprint requires a very specific way of looking at the problem. You need to decode the command words first. Is the examiner asking you to describe, explain, or write an algorithm? Each command word unlocks a different requirement. And before we dive into the exact framework that top students use to decode these questions, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so once you've figured out what the question is actually asking, you need a system to organize your thoughts. And that is where our first major concept comes into play. That system is called computational thinking. Now, the crucial point here is that computational thinking involves analyzing the task, identifying its individual elements, and planning logically before you ever write a single line of pseudocode. Think of it as your primary spell in your exam toolkit. It encompasses abstraction, problem analysis, and algorithm design. It is literally the process of overcoming smaller issues one by one, so that you naturally solve the entire problem. Top-tier students use this thought process to structure their answers. They don't just dump facts, they follow a framework. In fact, for written explanations of algorithms, many use the PEAL framework: point, evidence, explanation, link. They make a point about the logic, provide evidence from their algorithm, explain how it processes the data, and link it directly back to the scenario's requirements. This structured thinking is exactly what the examiners are grading you on. Section 2, mastering top-down design. Knowing that we need to break things down is one thing, but actually having a concrete method to execute that logical plan is another. Enter top-down design. Top-down design utilizes a critical computational thinking skill called decomposition. This is a real game changer. It simplifies a massive, intimidating problem into smaller problems or subsystems until each piece is sufficiently defined to be easily understood and programmed. This is often referred to in the Cambridge syllabus as stepwise refinement. The beauty of this approach is that it makes your final process incredibly well structured. Plus, in the real world, it drastically increases the speed of development because different subtasks can be handed out to individual members of a programming team. It even makes debugging easier. If your code breaks, you can fix one small subtask without tearing apart the entire program. When you're sitting in the exam, decomposition is your best friend. It takes a terrifying 15-mark question and turns it into 5 very easy 3-mark questions. You just tackle them one at a time.
Section 3, decoding structure diagrams. To properly map out these decomposed tasks for the examiner, you need to rely on a very specific visual tool. And this right here brilliantly illustrates the three foundational building blocks of a structure diagram: sequence, selection, and iteration. These visually organize your subsystems. A structure diagram expresses a system as a series of subsystems using these exact symbols. Listen closely, because Cambridge examiners are strict on this. A plain rectangle represents a sequence, meaning the code is executed left to right in the order it is written. If your code needs to make a decision, a selection, you absolutely must indicate that with a small circle in the top right of the rectangle. And if a process needs to repeat, an iteration, you mark it with a star in the top right. Remember our student Sam from earlier? Sam rushed and completely forgot to draw the star for the loop. Because of that one tiny missing symbol, the examiner couldn't award the iteration marks. Just remember, whenever you use that star, your iteration always needs an exit condition to avoid becoming an infinite loop.
Let's look at how this stepwise refinement actually plays out in a real scenario. We're going to build from a high-level task, like a school's lesson check, down into explicit subtasks. Look at the top level of this breakdown. We start with the main task, lesson check. We then decompose that down into the next layer, list of students, record presence, pass list to admin, and contact parents. But we don't stop there. We apply further stepwise refinement. List of students is broken down further into identify lesson and add students to list until all added. And notice that little star symbol there? That indicates iteration. The system loops until all students are added. Then look over at contact parents. It branches out into telephone or email, with those little circles indicating a selection based on a specific condition. You continue this visual mapping until literally no further decomposition can take place. If you draw this out in your planning space during the exam, you are basically writing your pseudocode in advance. Your mark potential goes from 0 to 100% just by mapping it out visually.
Section 4. The 4 design steps. Now that we understand the visual structure, we can adapt the classic computer model into a robust design process. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's dive into the 4 steps. Step 1, identify the inputs and outputs. If you don't know your required output from the very beginning, you cannot possibly define the process to reach it. Step 2, check for repeated inputs to select the appropriate loops for iteration. Will it be a for loop, a while loop, or a repeat until loop? Step 3, look at the required calculation or recording process, checking if you need if or case statements for decision-making. Finally, step 4, sequence the processes. Ensure everything is ordered properly, double-checking that items needing iteration are actually inside the loop, and single inputs or final outputs are safely placed outside the loop.
All right, it is time for an interactive workshop. I'm putting a mental 60-second timer on the clock. We are going to apply those exact 4 steps to a classic Cambridge exam scenario. A system requires exactly 100 numbers to be input, and it needs to output the highest number and the total sum. First, let's do a data scan. Look at the breakdown here. Step 1, identify inputs and outputs. We need to input numbers and output the total and the highest value. Step 2, are iterations known? Yes, exactly 100, so we lock in a fixed for loop. Step 3, processing. We need an if statement to check for the highest value and a running total calculation. Step 4, sequence. The for loop captures the inputs, but the final outputs happen safely outside the loop at the very end. Now let's play Find the Flaw. Imagine our student Sam wrote this code, but put the output total command inside the for loop. What happens? Exactly, the program would print the total 100 times instead of just once at the end. That's a classic error that loses marks. Sequencing is absolutely critical.
Section 5, translating to pseudocode. This brings us to the final transformation, where all of our visual planning becomes actual, executable exam logic. This is where the magic spell is fully cast. Notice how seamlessly the refined structure diagram at the top translates directly into the working flowchart and pseudocode below. It completely confirms that top-down design guarantees a well-structured final program. You can literally trace the boxes from the diagram straight into the pseudocode. We initialize our variables. Total, highest, and number are all set to 0. We open our for loop from 1 to 100. Inside the loop, we input the number, update the running total, and run our if statement to check for the highest number. Then, completely outside the loop, we output our final values. It works perfectly because the hard thinking was already done visually.
For our final challenge, I want you to imagine a 30-second timer. If you had to write a Peel paragraph explaining this code, you would say, "My point is that I used a for loop for iteration. My evidence it is the line for count equals 1 to 100. The explanation is that the system requires exactly 100 inputs to be processed, and the link is that this efficiently satisfies the scenario's data collection requirement without redundant code." Boom, maximum marks.
Section 6. The complete process. To wrap this all together, let's review the overarching framework that you must apply to any complex problem you face. Here is your cheat sheet recap graphic. We are taking your mark potential all the way to 100%. To guarantee top marks, you need a complete answering system. Rule 1, command word decoding. Always know exactly what the question is asking. Rule 2, Peel framework application. Structure your written explanations clearly. Rule 3, time management matrix. Plan your time effectively so you don't rush like Sam did. By methodically working through decomposition with structure diagrams, standardizing your solutions into pseudocode, validating your user inputs, and testing rigorously, you ensure your algorithms are not just functional, but reliable. And remember, an effective solution is also an efficient one. Always look back at your algorithm to see if it can be simplified, perhaps by combining multiple processes into one loop. Examiners love efficiency, and demonstrating it will absolutely elevate your final grade.
I absolutely love this quote from the source material. In effect, the essence of programming. Ultimately, mastering this methodical approach isn't just about passing your Cambridge exam or avoiding the mistakes that Alex and Sam made. It is the very essence of what it means to be a successful computer scientist. The pseudocode is just the syntax. The structural design is where the actual genius happens. When you master the design, the code practically writes itself.
So the ultimate question is, will you cast the right spell and apply this top-down blueprint to effortlessly dismantle your next complex programming challenge? I highly recommend you start practicing these visual steps before you jump into your code. Start with the structure diagram, define your sequence, selection, and iteration, and watch how smoothly your pseudocode comes together. Now listen closely. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.